School of Physical Sciences, Mridul, Mishra, and Promit. Yeah, so hello everyone. Sadly, introduced us very rightly. So today instead of waiting for the time, we'll be starting off with exoplanets. You must all be fascinated with that. So yeah. Okay. This is the roadmap for today's talk. There will be parts, then Q&A, and surprise. We'll be dropping some feedback or questions on you, and you have to answer. At least one hour, please. Okay. So over drops. So, what is an exoplanet? Okay. So, exoplanet is a planet that orbits around a star other than Earth. That is, it is a star. It's a star that basically not our sun. So any other planet which is not in our solar system is an exoplanet. And also this stands for exosolar planets, but we don't usually write that. So just keep that in mind. It is beyond our solar system. So exoplanets can be detected by various methods like indirect methods like transit depth, radial velocity, gravitational microlensing, or direct imaging. Also, the exoplanet sizes ranges from suburbs to many times of radius of Jupiter. So there is a variety of radius. So you can understand that many times the size of Jupiter means immensely large exoplanets. So why study them? What is the need for studying exoplanets? Exoplanets are normal things, right? So what is actually the need to study? So we need to study exoplanets to understand the different types of planetary formation, to know various how many various ways planets can form. Like you must have studied the various types of planet formation, like gravitational instability, core accretion. So as we study more and more exoplanets, we will get to know how actually planets form. Also, our main target is to find signs of life, right? So as we study more and more exoplanets, we will be more sure that we are the only ones that we exist or not. Also, as we study more and more exoplanets, we can use those planets as a reference to study other planets. Like we will get more reference points, right? So that will be a good thing. Now, a question: are there more planets than stars in our universe? What do you guys think? Yep. And why is that? For a planet, you need a star, right? True. That is under the assumption that the accretion disk is big enough. Yeah. So yeah, but technically you are correct. So yeah, both of you. Nice, good. So we do have like more planets than stars, and that does make sense because usually the accretion disks are big enough. You can have like many planets for a star, but not many stars for a planet, right? Oh, that can be the case. So if you have a binary system and just only one planet, I don't know the example. Many stars for one planet. Can be possible. But mass of planets would be much lesser than as compared to star. If I'm not wrong. We'll take some more questions later. Let's get it. So, as I said, we need to study more and more experiments. And as the proverb says, charity begins at home. So, we will study, should first study the Earth's closest neighbors, that is Venus and Mars. So, here is a quick comparison between Earth, Venus, and Mars. So, in Earth, as we know, it is nitrogen dominated. It also is liquid water. And as we know, it is the only habitable planet till date. So it has, of course, strong biosignature potential. Whereas in Venus, the atmosphere is quite dense and it is mostly CO2 dominated. Also, it also has runaway greenhouse and it also has a high albedo of 0.75. That is, it has a very high reflectance. You would know about albedo, right? So, whereas in Mars, the atmosphere is very thin and that's why the surface is quite cold. So the runaway greenhouse effect doesn't dominate.
why Venus is the hottest planet despite having a high altitude. Isn't that counterintuitive? Like you're reflecting most of the sunlight that is coming to you, but still you're the hottest planet. How is that possible? Any thoughts? You dominated atmosphere. True. Very bigger also. Yeah. Sure. So it is essentially a trap that traps in all the sunlight that's coming in. So even when it is, reflecting a significant portion of it, the greenhouse effect is quite strong there. That is why it is still the hottest planet with around 700 Kelvin of temperature.
It is also due to runaway greenhouse effect. Do you guys have runaway greenhouse effect?
No, sure. Runaway greenhouse effect is something which I can introduce. So let's say if we have, okay, I won't draw. Let's say you have an ocean. You have solar rays coming in, and the water is turning into vapors and it is getting trapped. Now the water vapors will trap more and more incoming solar radiations, and that would increase the temperature. Then you have more water forming into vapors. That is how this chain reaction begins, and now you basically have a trap where the temperature can only increase if you do not have any other effect.
So this brings to the next slide.
Isn't that mesmerizing?
As in zoo, we see different types of animals. So in the exoplanet zoo, we see different various types of exoplanets.
Yeah, the ones we're looking for are here, the green ones. So these are in the habitable region, somewhere here. Those ones are way too hot, these ones are way too cool. So yeah. Why it's nothing. This is just like planet spirit. Yeah.
This graph you may have seen in the course. So can you can anyone explain this? What can we infer from this graph? Any idea?
Planets will form. Yeah, sure. We'll learn out.
Most of the planets are discovered by Kepler, which has a bias to detect nearby planets to their star. Because so planet.
Also, you can say by checking the x and y axis.
Same size are
This is the main reason that we find mostly Earth-sized exoplanets. Because see, the dense region is in the comparable range of radius square. Also, the orbital period is around 5 to 100 days. So it has very high orbital speed.
Especially for me, this region is very interesting. So I'll come to that in a moment. The region between Earth and Neptune. You see that very densely populated.
And anyone knows about Kepler's space mission? Right? Because it is there.
वो आपको आपके साथ में प्रोजेक्ट करता है वो क्लास में सर्च करता है इन वीडियो
Sure. Okay. Now, to find the science of life, we must have experiment. We must know what else, what we have to find to get the science of life. So, we generally detect these gases like oxygen, ozone, methane, or water vapor, or carbon dioxide, nitrogen dioxide, many others. So, coming to oxygen, many people have this notion that as oxygen sustains life, so it is the most important biosignation. But that is not the true thing. Because oxygen may have some abiotic sources like when carbon dioxide dissociates, it dissociates into that's good. It dissociates into carbon monoxide and nascent oxygen. And these nascent oxygen combine to form oxygen gas. Similarly, in the surface, when oxidation reaction happens, it also forms the nascent oxygen and thereby oxygen gas is formed. So that is of course a false thing that right. Sorry. Now coming to ozone. Ozone is formed by photochemical catalysis of oxygen. When UV rays fall on oxygen gas, it dissociates into nascent oxygen, right? And oxygen combines with the nascent oxygen to form ozone. And a good thing about ozone is it is quite easily detectable in thermal emission or any form of spectra like transmission or thermal emission spectra. So it is quite better detected than oxygen. So it is easy, right? Now coming to methane. Methane can be formed without light. It can be formed. It can be present in the surface. When, but when we see methane along with oxygen, it is the it can be a sign of because when methane occurs with the oxygen, it vigorously reacts with it from carbon dioxide and water. But when we see methane and oxygen for a longer period of time, then there is a sign that something must be present that must be replenishing it to keep both of them at the same range. So that can be a method. Now coming to water vapor. When we see water vapor in the atmosphere, we can think of what? Water cycle. So if water cycle occurs in an exoplanet, it can mm, it can depict that the condition and habitable at least for us. Our main goal is either to our main goal either is to find signs of life, or even if we don't find signs of life, actually we need to find habitable conditions for us because global warming and if Earth gets destroyed, then we need to find a new home. So what
But don't destroy it.
now coming to carbon dioxide. Carbon dioxide is mainly dependent. Carbon dioxide mainly controls the greenhouse effect. Now, many of them have this notion that greenhouse effect is bad, right? Because it causes global warming and destroying Earth. Right. Okay. But this is not the truth. Because carbon dioxide increases the temperature to a certain level that makes our surface habitable. Similar, for example, if carbon dioxide would not have been present, greenhouse effect would not dominate that much. Then the temperature would have been right to 55 Kelvin. But because of carbon dioxide, this has increased to 33 Kelvin, and now the effective temperature is 28 Kelvin. You must have studied this. Now, these are seasonal signatures. The I covered the biosignatures that can be detected from gases, and these signatures have to be studied for a longer period of time to get confirmed that there may be a sign of life because of this. So, seasonal CO2 fluctuation due to plant growth. You may doubt that why CO2 is required for detecting the light. The answer is in summer the photosynthesis rate is more because the vegetation is of course much more. So the as plants do more photosynthesis, they absorb CO2 to much more extent. So there is a dip in CO2. Whereas in winter, when the plants die up, they release CO2, and thereby there is a spike in the CO2. When we detect this over a longer period of time, that dip and spike, so we can get the idea that there is a chance of variation. Now, coming to vegetation drainage. Anyone knows about vegetation drainage?
Why are plants green?
First question, why are plants green?
They reflect the gas. But what are they absorbing then? They are absorbing light. Yeah. I'm not very sure. Like, I'm not a biologist. But yeah, he can answer that probably.
They absorb red, mostly red. And a starting fact is that above red, that is like NIR, near infrared range, they mostly reflect it. So there is a when we detect the spectrum, there is a spike in the NIR. So from that we can understand that there is a something is present that has chlorophyll, because chlorophyll has this feature to absorb red light and reflect in the NIR. So it we can detect this in 680 to 759 nanometers. That because the red lies in almost 700, right? Because visible is from 400 to 700, so that is. Now, seasons. In summer, the season, in summer, the vegetation is more, right? Because of photosynthesis, I said, the plants are, the climate is favorable for plants. So, the vegetation is quite more. So, we would get much more CO2 and vegetation release. So, there, and in winter, there is more ice or snow over the world. So ice or snow has the characteristic that it has very high amplitude, that is, it reflects much more. So we would get a much brighter spectrum. So when we detect this dip and the spike in the brightness over the period of time, so we can understand that a seasonality cycle is occurring in that district, and obviously that replicates the Earth, right? So if we can sustain, we can live in that, live in Earth, then we can live in that. So that is a. Now, clouds, albedo, and climate effects. Clouds play a great role in detecting the signs of life because
But wait, what do actually clouds do? Like, it is seeing a person, but they are wearing a mask. If you try to detect only the surface features, what you would end up with is, like, if they're wearing a green mask, you would say that their face is green. So we don't need to detect what the cloud is made of. We do need to a certain extent. But what we actually need is the surface conditions or the surface temperatures. Yeah.
now cloud reflects most of the light. So cloud is responsible for having high albedo of an exoplanet. So when we detect the data, then because of reflection of light from the exoplanet, we may get errors. We might not get that original data. So it is actually masking the features. That's what we said. So that is actually a barrier. So when we collect data, so we try to remove those clouds. Many instruments like AIRS, that atmospheric impact sounder, uses cloud here radiant. That is that it has the ability to remove the cloud beforehand, so that we can get a better set of data. And then is the planetary albedo. The planetary albedo, if the planet has a high albedo, then it has of course of course very high reflectance. So the brightness will be much more, and as the brightness will be much more, the equilibrium temperature will be less because it is reflecting the light. So solar radiation is not reaching the surface. So the surface will be much colder. But the planets with low albedo will have, of course, hotter temperature of surface because they absorb most of the solar radiation. Now, for phase variation, the phase variation is just like that. In full phase variation, the planet seems much brighter than the crescent variation. So it
Because it's such far distances, you cannot actually see the faces, but rather their brightness. Because if a star is a point object, imagine what a planet is. Another cool fact, on some exoplanets we have diamond or glass rain as well. So technically wood is more valuable in the universe than diamonds.
transit. Many of us study that. Okay. So I have now explained that using Earth around Sun is much tougher job to detect because you may know that formula of transition, that is change in flux by actual flux is equal to radius of planet by radius of star. So if we keep Earth's radius and Sun's radius, you can see that the signal is coming quite less. It is quite less. He is drawing the graph, and so to detect that, we need very sensitivity. that could detect even that uh, tiny signal much precisely. So another, what type of star is, does anyone know? You have studied this. Yeah. So that's why it is much tougher to detect the signals from Earth around Sun, because the Sun is much bigger star. That's why it has a better detectability around M dot. Do you remember that size range? MKGFABO. That's why M is much smaller. So when we plot that in the radius of star, so that signal will be much higher. So as the signal will be much higher, so it will be better to detect, easier to detect. Right. Now, these are some spectra. When we try to detect an exoplanet, we have actually these three major spectra: transmission, emission, and reflectance. So, what is transmission spectra? Transmission spectra is the star type that is filtered when the planet transits around the star. You have studied that, right? So, it would be, of course, best for those planets that are around bright star. So we would get much better data. Also, what does transmission spectra tells us? It mainly tells us about the gas composition of that exoplanet. And now for emission. Emission is the planet's own thermal emission. That is, it is the heat radiated by the planet. So to detect that, we actually calculate the brightness temperature of planet along with star, and then subtract the brightness temperature of star. Because when the planet is transiting around the star, let's say, then when I can draw, yeah, sure. So this is the star, right? And this is the planet. Probably. Okay. Now, when we now when we get this, we get the brightness temperature of the planet along with star. But when it revolves around the star in opposite, that is the planet, exoplanet is opposite the star. And observer, here is the observer, here is the star, and behind that is our exoplanet. Then we can get the brightness temperature of actually the star. So we can easily subtract it and get the brightness temperature of only the planet. So that's how we detect the thermal emission of that planet. Now, it is, of course, as it is related to thermal, so it is best for those planets which have very high surface temperature. Because as the surface temperature, if the surface temperature will be high, then it would radiate much more. So we would get better signals, right? Also, and tell what does it tell us? So as it is related to thermal, so it would, of course, say about the surface temperature. We would get an idea. And also it has the ability to detect some of the major gases present in that surface, because it is we are getting the idea of the surface of the exoplanet. So we can also get the idea that gases present in that surface, exoplanet surface. Now coming to reflection spectra. Reflection spectra is generated by the sunlight that bounces off from the either the surface or the clouds, because clouds have much the property to reflect back the sunlight. So we can get that reflection spectra to that. So it is best for those planets that lie in the visible or near infrared range, because there the reflection spectra would much dominate. In thermal emission, it dominates in the infrared range, because you know that infrared range is much related to thermal. So that's the thing. Now, what does it tell? It tells about the cloud as the is reflected from the cloud or the surface. So it obviously tells us about the cloud, how is the cloud, or how distributed is the cloud around the atmosphere. It also gives an idea of the surface, whether how much it is reflected, how much does it reflect, and also the overall planetary reflectance, that is albedo. It also gives an idea. Now, what is JWST? My first question. When it was launched? This is not business. This is not, but still, if anyone can answer.
Okay, these are just facts.
Nah.
Okay.
Wait, isn't it 25th December 2022?
2021.
Oh, okay.
And currently it is in India. Now, how we use JWST to mainly detect. I didn't use it to in my internship. So now it is very sensitive in infrared range. So as I said, the thermal emission is better in infrared range. So it is good for thermal emission. And it has also the ability to detect some of the atmosphere gases. As I said in thermal emission, it has also the ability. Now, it is also able to detect the transmission spectroscopy around the M curve because it is not much visible around G type or more because the signal will be quite less. That's why it is written sun-like star is very high because sun is G type star. As you know. Now, its detectability. It is limited by instrument noise. Instrument noise means readout noise or thermal noise because it detects photons, right? So it has to be kept at a very cool temperature, like 40 Kelvin, so that it can detect. Otherwise, much error. So it has some instrument noise and also the star activity. If the star is variable, it is quite harder to detect it, right?
So you all know what variable stars are, right? Or you don't. So stars also go through a cycle of their flux changing, their intensity is changing. Our sun has a cycle of 11 years. So you will find it being not significantly bright or dull to us, but someone who's observing at a far enough distance, they would observe that, okay, the sun is more bright during some phases. And so basically this thing you see, right? This is a straight line only when the star is emitting constant flux. If that flux is changing, you would see like increasing or decreasing things here as well. So if the star itself has a decreasing flux, you don't mistake that for a transient. You have to make actual observations.
Why does that happen?
Because the flux itself, okay, by the star.
Why does that happen in the star?
Oh, that is interesting. So that probably has to do with some nuclear physics. I'm not very sure about it.
Might be.
For our sun, there will be 18 phases. So 8 planets and many asteroids also.
What?
The target. Let's get to the sun.
There are many assumptions that we make in transit. We can talk at length after this session. This formula that you see is not pretty straight. There are multiple things which you can point out, but I would explain to you later.
Now, the fundamental question. Why are we even using Earth as a benchmark? Why not any other thing? Like Venus, Mars, Mercury? Of course, still like. And the main thing is, we have a larger data set. We will, of course, use that that is a right. So, Earth provides a real data point. When we are modeling spectra for other exoplanets, we need a good reference. So, when the spectra is made, we can validate that through Earth spectra and check if it matches, replicates with Earth. So if it replicates with Earth, then the conditions are more or less habitable. At least, even if we find that I discussed before, even if we don't find that, the conditions in that exoplanet will be habitable. That will be beneficial for us in future.
The models here are basically the CS framework, the coding framework that we use. We input some data based on observations and then we get an output which would make sense.
It also helps in training of algorithm that will be beneficial for future missions. Like JWST was a mission, ELT is a mission, that is extra large telescope. And in 2029 tentatively, Ariel will be coming. For that, these are some of the missions. For that, we need to train the algorithm based on the, because if we don't train it, then it will have actually a problem, right? Because Earth has a large facet and that.
Sure. So, what if I told you that the most common exoplanet that we see is not in our solar system?
That's the thing.
So, okay. Anyways, we proceed. I'll come to what they are. They are super Earths and sub-Neptunes. So, what do I mean by super Earths? The first thing that comes to your mind, the name is pretty simple. It is self-evident that it is just like Earth, but it is bigger. So the radius size would vary from 1.25 to, but there is some ambiguity. I'll come to that later. Then we have sub-Neptunes, which are, as the name suggests, Neptune. So this is a visual to help you. This is Neptune. This is a comparatively very big. This is super Earth. So it is just like Earth, but it has like a bigger size that would. Sub-Neptunes are also called rings. So you have basically a bigger envelope of atmosphere around it. There are certain differences in their atmospheres too, but we'll come to that. Yeah. Why do they matter? Why are we talking about that? Do you have a question? So, what? Ah. Hmm. Yeah, that does have. So there we basically plotted the radii and the orbital period was on the x-axis. So that is why these are quite densely populated. Like you would find various populations of these. We are probably just unlucky to not have one because had we like if there was one nearby, we would have sent a probe or something and we could have gotten like very useful data. But as luck would have it, we don't. But yeah, that shouldn't depress it. We are resilient. Yeah. So this is just to give you perspective. More than 5,000 planets were found, and 21% were super Earths, 35% were Neptune like. There is an ambiguity. At what point, at what atmosphere would I call a super Earth, and a sub-Neptune, sub-Neptune? There are also differences in their atmosphere composition. So super Earths would have like probably more CO2, and some Neptunes would have more HE or H2. But then there lies some ambiguity. So you would find a planet being labeled super Earth in some papers and a sub-Neptune in some others. We have to figure that out. We will. So yeah, this is one of the planets which you must have heard of, K29. How many of you have heard of that?
It is quite a high, right?
Okay, so if you don't know what high was about, it was that they basically found DMS or some other biosignatures. So DMS is dimethyl sulfide. I presume you will know that. So that is some have known abiotic sources. That's something that is produced by life. But then those claims were falsified. So we do have images for that. Sure. So you can read more on physics or and NASA's website. If you want, I can share the links later. The previous one. No, the previous one. So another one is Kepler 22b. We have EOI 700b. Sure, we can proceed. So what? DMS, dimethyl sulfide. That is like something which has no known characteristics. So something that only living beings produce or living organisms produce. That is from where you can find like
I think cabbage you can find. Like,
yeah.
it was in the slide.
Or have you not studied that? You guys already have the slides.
Biotic source was cabbage and abiotic source was not known. So when we found K20, there was a hope that we will get.
There were initial claims values, but then we ran detailed analysis and we found that okay, that is not the case. In fact, water oceans are also not there.
There's no DMS there actually.
No, like not significant. It's something you would not call significant. Yeah. So before that, I did talk about atmospheres, right? And we could not differentiate between what they are. So how do we differentiate between atmospheres and why does the super Earth have like a smaller one? Also, do you guys know that Earth should not have an N2 rich atmosphere, an N2 rich atmosphere? Yeah, there is no. See any other solar system, any other planet in the solar system, you won't find significant amounts of N2, and that is certainly not in the accretion disk. How did we end up with that? That is still an open question. We don't know.
Like most of the planets are either hydrogen or helium.
Yeah. So now coming back to this, NDC. So as you would know that we have accretion of planets happening, and then gas accretion starts at some point. That when forms an atmosphere around the planet, that is called the primary atmosphere. Primary because it is the first one being collected, and it is mostly of hydrogen H2 by hydrogen and H2 and helium. But then we have atmospheric loss. How does that happen? That happens because of the star's stellar radiation coming in. So we have that. Then, if there are elements available or if things dissociate, they would probably go away. And if not, then they gain kinetic energy, and that would push them away. Because initially they were accreted because of the gravitational pull of the planet. But then when we have full atmosphere loss, then we end up, having some outgassing. So you have a very thin atmosphere or probably no atmosphere, and then the interior of the planet starts to, dominate the atmosphere. We will be coming to that. So interiors. Yeah. Yeah.
Are you saying that the forming of atmosphere is happening like only for overbreaking purposes, or are you saying that even for description it needs to be somewhere around? Yeah, it's
Oh, for disk instability, there would be something else at play. This is for the core equation part. This is for the core equation. So yeah, the interiors, as I mentioned. Why do we need to study that? Because gassing is what forms the secondary atmosphere, and that would also explain why we have life on Earth. Because if you do not have a suitable atmosphere, you won't have life here. Now, there is one term I need you guys to know, which is gassing. So you can think of gassing for practical purposes in equations and all. So the basic intuitive sense is the escaping tendency of a gas. But if you want to use it mathematically and understand like what it actually means, then you can think of it as a correction for real gases. So in the ideal gas theory, we thought that okay, things do not interact; they are of point sizes, all the good stuff. But reality is much different. How do we cope with that? We use the fugacity instead of pressure. So oxygen fugacity certainly plays a very significant role because that would shape the atmosphere, the conditions, the chemical conditions. Now that is determined through something called an IW buffer. IW buffer is iron phosphate buffer. So this thing here is iron, obviously, and here phosphate. Depending upon how much oxygen is needed or what the environment is, they can shift phases. So like,
Do you guys know what boosted is?
yeah, you can probably just say that it's iron oxide. But these X is probably due to some effects. Like you would have studied of shortly or other yeah. Flat effects, probably shortly. But then we cover like generalized stuff, yes. So we define oxygen fugacity relative to the buffer. This is on log. So we end up with three readings, mainly three readings. The first up would be the reduced mantle. That would be like how would you identify that this is a reduced mantle? You cannot see the mantle, right? You can only study its atmosphere. So to determine that, you would look at its atmosphere. If it has significant amount of hydrogen and H2O, then you can call that to be a reduced mantle. You can probably think in that way. Because as you would know, in this region also you would have significant amount of hydrogen and H2O. So you have to look for other gases. CO2 would be present in very less quantities. But as we shift to the intermediate region, we would see a spike in CO2. Now, CO is another such gas. COS would be observable in trace amounts. That is something that would differentiate these. And for the other region, we have the oxidized mantle, which would then again have more sulfur compounds.
Can you explain once again what is are we mean by oxidized mantle?
So the mantle, like the oxygen fugacity relative to the buffer is more there. You can think of it as having an oxidizing environment, having much of oxygen in the environment. So if you probably try to, you know, make a reaction, try to do a reaction which involves oxygen, that would happen very vigorously. That is what I mean by having an oxidized mantle. Because all the reactions are taking place inside the mantle. A melt is forming, which we call lava when it comes up. And this melt, what reactions occur in this depend upon the mantle fugacity. How much oxygen is there in the mantle? Yeah. Proceed further. Habitability. That is what all of this is about. Super Earths are mostly rocky, as I showed you in the diagram. So we want to find something similar to Earth, like some conditions which are similar to Earth. Of course, sub-Neptunes, the thick atmosphere has its challenges, and we cannot probably analyze them in that way because it has significant amounts of H2 and He as well. But there are some challenges due to the star as well. Like he talked about having a bigger star. I'm talking about an M rover, but that being more active, like having flares, tidal locking. Flares again would change this. If you have a flare, you would see the flux probably increase at some point, and then and tidal locking, if a planet is not rotating, not revolving around its axis, that would create like a fireball on one side, probably melting, and the other side freezing, and there would be constant evening on the sides, so on the ceiling. Yeah. That is the neat part. We don't. That is why we make models. That is why we analyze it through them. This is just the neat theory, the ideal case that you're studying. In actual footage, if you try to measure it, it would come out to be something like this. Then a dip and then increasing further. So you would have an overlap of the star's own activity changing the flux. That with the planet. Yeah. Yeah, there are solar flares, but how Earth protects us? Thank you for raising that question. Earth protects us through its magnetism. We have very strong magnetic field. That is why even solar flares or stuff like that turns into auroras, and you see it beautifully. But if our planet would not have had that, then our fate would have been something like Mars. So all the atmosphere blown away. Oh no, we currently don't, because how do you do that? That was an interesting question that but that is quite less. Like for galaxies or for stars, you can study that. Oh, that's interesting. So you are saying that we can probably detect.
I'm not sure if that's what they use.
No, I'll look into that. So if a planet has a significant amount of magnetism, then that it would be okay with less. Tidal locking, as I told you, and then we have the day and night differences. But life is possible on the twilight zone, where there's constant evening. Now, as you already told you about JWST, I'll also tell you about HST. So, like the predecessor of JWST, Hubble Space Telescope, they also found Neptune and sub-Neptune gas planets, H2 detections, And currently, JWST is expanding its sample and wavelength coverage. Yeah.
Number cool planets. To aliens, Earth might just look like a pale blue dot with hints of just oxygen and water. So it is not like just as it happens in the sci-fi movie, they attack on us. It is not like that.
We are not that special.
They might find volcanoes, dimethyl sulfide.
They have that signal.
If they thinks that EMS is the source of life, I mean, characteristic of presence of life, might find that.
Probably, but then detecting Earth is another challenge, right?
Yes.
That is what we told earlier. That okay, if it isn't like we have a star, that is you
The
have
first challenge will be detecting Earth around the sun. Then the second challenge will be detecting demons.
Yeah.
So they must be much advanced.
Now first we ask questions and then so proceed. Which is the most important for life on planet? Its size, its distance from the star, its atmosphere, or all of the above? This is quite subjective. So once I'm
You're free.
yeah.
Even if it has like good size, proper atmosphere, if the distance is too far, that's not going to be life, right? Temperature is a thing. All of them. So proper distance is most important. But like life is not a thing where you can like say if you just have a lot of this happens and that's a balance.
And again, we are looking for life as we have there on Earth.
Yeah.
If you find a new form of life, how would it detect that?
Most important, but all of the
So like that is detected, that is perspective based. Whatever you would consider, but yeah, given time, even life on the planet that you would like, which is very far away, it can probably trap enough heat and become warm enough. But if it is very far, then we don't. The answer is we are looking for it.
Okay.
Yeah.
I had asked sort of previous class that we are searching for light on Europa and on
Yeah.
different planets. They are not Goldilocks zone or current distance from the sun. So Sir said that they are in fact looking for light beneath the surface of the planet. So is the distance from the star really as significant as we are?
That is what I told. That okay, it isn't. But in some cases, it might be. Like if we have some sort of a super Earth, for that it might be pretty significant because if you don't have it close by, then it would probably freeze and die out. But if you have something like Europa which has ocean beneath it, then life can exist. If we have a sub-Neptune that is that has a thick enough atmosphere, then like, it can probably trap in enough heat. Then we can have life. Yeah. If aliens studies Earth's atmosphere from 50 light years away, they would be 100% sure that life exists here. What?
Yeah.
True, true. Again, subjective question. Just to stir some thoughts.
They could never be 100% sure, right?
Why can't we? They can probably send spacecrafts. We don't know.
Their spacecraft speed might be much larger than we can even think of.
Natural or artificial, how can they
What the satellites of a planet, the exoplanet. I think that if it is an exoplanet or not. So if a debris is that big, then that is a planet, bro. If we have very small debris, that won't impact this significantly. Because another thing I did not mention here, or which none of you noticed, was that we are not considering the distance between the star and the planet here. If you have ever seen a solar eclipse, you would know that the moon is not as big enough as the sun, but it still covers it. Why did you ask the same question when I wrote the formula to be r of the planet by r of the star? Where is the distance?
Distance doesn't matter.
Exactly. So, to answer his question, he asked that okay, if there's debris, how do we separate that from the planet? So if that debris is big enough, then that is a planet. And if it is not, then that is insignificant and we won't observe that. Yes.
It's an open question. What's the most beautiful exoplanet that you can imagine as a planet?
You know, to end things on a good note.
What do you mind?
It can have a type of light much different from what we see here.
Say maybe advanced.
True. So things are not always about us.
Earth is the best.
True. True. Indeed. That is. Like wood actually is more rare than diamonds. You can find actual planets that are basically diamonds, but that's not valuable. Not as valuable as wood. Yeah. True. Yeah. But then again, we are looking for complex life, something which can understand like it exists. Yeah.
As of now,
Like,
we are
any life is good. But yeah, sure. You did.
as of now we are just taking the organisms that are present of Earth, present Earth, because our thinking radius or like our thinking goes that we see around. We can't think anything abstract.
I get that when we space mission contains like dash so they are that we have contaminated the water.
Why contaminate? Like it is good.
But contaminated will make sense if they can survive. If they crash on moon and die, then it's of no
It
use.
says that species.
Yeah.
But we have exciting things.
So here on this, you can refer to these papers, or you can also ask us later on. And now it's time for questions.